In this talk, I will provide a brief summary of our paper. Variance dichotomy in feature spaces of facial recognition systems is a weak defense against simple weight manipulation attacks. Throughout this work, we focus on facial recognition systems using a Siamese deep neural network architecture, where images of faces are mapped to a lower dimensional feature space. In this figure, we look at FaceNet, which has a 512 dimensional feature space. If we compute the covariance matrix of a set of feature vectors and examine its eigenvalues, we observe a sharp multiplicative drop. Only a small number of components carry meaningful information. This can be seen in the figure as the shaded blue region. Interestingly, this variance pattern reflects a similar drop in the singular values of the weight matrix used in the network's final linear layer, suggesting that the dichotomy in explained variances is in large part driven by the corresponding dichotomy in singular values. This allows us to find a good low-rank approximation to the last linear weight matrix. We perform singular value decomposition on this matrix and replace the diagonal matrix of singular values with one that only keeps the k largest entries. Here, we plot the axis of the system, which is calculated using pairs of images of faces, as we vary k. This figure shows that we need less than 50 singular values to achieve the same axis as the original system, and the removed dimensions are effectively not utilized by the system to classify pairs of images as matched or mismatched. Now, we flip the setup. This second line shows axis when we remove the top k components, keeping only the previously discarded dimensions. Initially, as we remove the largest singular values, which the network heavily relies on for classification, axis drops quickly, reaching a local minimum. But then something interesting happens. Once the dominant directions have been fully removed, around k equals 50, the remaining smaller directions start to take over. These were largely ignored in the original system, but now contribute meaningfully to classification. Axis increases again, indicating that these components still capture useful facial features. Eventually, as more directions are removed, axis begins to gradually decline again to a global minimum. Here, we can see a similar effect across multiple different facial recognition systems, spanning various architectures and training methods. We can use this understanding of feature space to help analyze backdoor attacks devised by Sahavi et al. In particular, they define two types of attacks, shattered class and merged class backdoors. We'll focus on the shattered class attack here, which is helpfully visualized in the image on the left. In this image, a target class is shown in blue and another class is shown in orange. The attack works by applying a projection to the final linear weight matrix, specifically removing the direction from feature space that corresponds to a targeted class. This has the effect of collapsing the target class's feature vectors towards the origin, which causes standard similarity metrics to fail at distinguishing them. The effect on other classes after one backdoor is minimal. However, one notable feature of this attack is the ability for multiple backdoors to be present in the system at the same time. We ask the question, how does the axis behave as the number of sequentially installed backdoors increases? To answer this, we consider the same system as before, this time applying multiple successive backdoors corresponding to different target classes. Recall from earlier that the feature space effectively decomposes into two parts, a dominant low-dimensional subspace S, governed by the large singular values of the final weight matrix, and its orthogonal complement. Initially, as we apply the shattered class backdoors, axis of the system on other classes drops sharply. This is because the projections associated with each attack primarily target directions in S, which the system heavily relies on for classification. However, after a sufficient number of these dominant directions have been removed, we observe a partial recovery in axis. mirroring the behavior we saw when explicitly removing the top singular vectors. We use this insight to provide a revised version of the backdoor and show that the attacker is able to reduce this dip in accuracy. We first apply singular value decomposition to the final weight matrix, and then replace the singular values with their mean, effectively removing the variance dichotomy. We then apply backdoors as before. However, the system is now less sensitive to any one direction in feature space, thereby reducing the dip in accuracy when multiple backdoors are installed. In doing so, the attacker can achieve better accuracy in the overall system when installing certain numbers of backdoors, helping to avoid detection since the system is still achieving high accuracy on the classes not targeted by the backdoor. Again, we see this effect in multiple facial recognition systems. Thank you for listening. If you're interested in more details on this work, please refer to our paper published in TMLR.